Welcome to the third episode of Thinking Like X, a podcast by ThinQ. I'm Madhav. In this episode, I interview Adam Disque, an environmental engineering master's student at Texas Tech University, who earlier served in the US Air Force as a bioenvironmental engineer. I met Adam last summer, that is 2019, when he was interning at Raytheon in Tucson, where I'm doing my PhD. In fact, this episode was recorded then. While most of the people we have interviewed and plan to interview on this podcast are well established in their field, Adam isn't as yet. He's a student. However, he makes up for that with some very useful insight into how engineers think. Added to that, his experience in the US Air Force makes the discussion even more interesting. This episode is titled Thinking Like an Engineer. Engineering is something ThinQ does not currently have expertise in, but we do eventually want to expand into engineering education. In order to facilitate that, we will have a number of engineers on the podcast. In fact, we do have another episode already recorded with Vidur Kaushish, my cousin, who is an aerospace engineer in California, who has just started a company which facilitates the launching of satellites. I hope you enjoy this episode. Towards the end, Adam narrates a particularly interesting experience while at the US Air Force. While it isn't strictly related to the topic at hand, it was too interesting and scary to not include. So let's begin. Hi, I'm Madhav, and with me is Adam Disque. Okay,
That's right.
That's right. Adam is an engineer. He's doing his master's at Texas Tech. And he's currently interning with Raytheon over the summer. He was earlier in the US Air Force before starting his master's, right?
Yep, that's all right.
Okay, perfect. So we were just having a conversation before we started recording, and what I wanted to ask Adam was, so we want to take an engineering problem which you've worked with, and see how you went about attempting to solve that problem. What were the things you kept in mind, and so on?
Yeah, so part of the training, I guess, at least being an engineer, is essentially everything we do is problem solving. So to me, it's just like doing your regular job. But at least when I was in the Air Force, the way that I kind of learned how to problem solve was essentially through this thought process of identify, analyze, and control. And so that was essentially how we addressed every problem. First, we wanted to identify what it was we were looking at, and we wanted to analyze it by either collecting data or understanding the data if the data is the problem itself. And then controlling it could simply be learning how to use that data, or to solve the problem, or in some cases to mitigate a health risk issue. So, for example, when I was in the Air Force, I did bioenvironmental engineering, and on the state side, we did a lot of interesting things related to industrial hygiene and preventative medicine. But when we would deploy, we had kind of a response capability. Essentially, our job was anytime that an unknown threat would come to a base, they would, halt all operations, they would cordon off the area, and then they would send in units like me to figure out what it is. So like this one example that we had, we were somewhere out in the Middle East, and there's a random truck, this little bitty tiny white pickup with a bunch of barrels in the back, drove up to the main gate of this base. And the security people tried getting him to turn around and to leave, and he got flustered, and this individual just got up out of the vehicle and left. And so they freaked out. They were like, why would this person just leave a truck? And so they shut it down, and all these EOD people did their thing to make sure it wasn't explosives. But at the end of the day, we eventually wanted to figure out, what's in the back of this truck. So I was able to respond alongside the fire department, and we set up this big decontamination tent, and we hopped in these level A suits with some SCBAs, which is like a breathing apparatus, kind of like what the firemen would use going inside a house. Okay. And then we basically we grabbed some of our gear. We were trained in how to use things like a hapsite, which is just a backpack version of a mass spec. And essentially what it does is it just draws in air samples, and then it slams these particles in this, like, we call it like the easy bake oven. Not to get too specific or anything, but essentially what it does is it just tells you what the chemical makeup of it is. And so we went out and collected some liquid samples. In this case, it was a liquid. And then we brought those liquid samples back, and then we ran a bunch of different tests. It ended up being just a bunch of like petroleum waste, nothing too crazy. But it was still really strange how this individual just like abandoned this truck at a base. It really got everybody bent out of shape. So that's just kind of an example of like, through training at least, like what was the problem? Well, the problem was that this truck had showed up with an unknown substance in the back of it, and we had absolutely no idea what their intentions were. Were they running out of gas? Why the heck did they show up? Nobody knew who they were. And then, so that's kind of the root cause. And then the next question was, we wanted to prioritize what's that waste. And so then that's when we identified it. Once we had identified it, now we have the data. And then we, based on our experience, know what to do with that data. Like if it was explosives, we would have completely done something different than when we found out that it was just sludge.
Okay.
Since it was sludge, we were just like, oh yeah, not a big deal. We know how to get rid of that. And so, and that's just like one example of something I experienced in the Air Force, at least.
Okay. So it seems like one of the things which seems to be important for this sort of problem solving is you need to have a relatively good understanding of some different areas. So, for instance, you need to understand what the chemical makeup of things is, right?
Absolutely,
because
yeah.
you need that understanding. You need if it was something else, you would need to know about explosives. You would need to know about all of these different things. So there's a mixture of biology, physics, chemistry, and so on. And I guess to an extent you're trying to figure out why this person left. So there's a bit of psychology and so on which get into it as well. Okay, so let's take another example just to illustrate a little bit more.
Let's see. So before I had interned at Raytheon, nothing really special goes on there. It's really just just production basically. But another place that I interned was actually at General Dynamics. And I was actually interning in an area that is related to what I'm going to school for. I'm going to school for environmental engineering. And a couple summers ago, I had the opportunity to be an environmental engineer at this particular manufacturing plant. And the problem was that so this example is related, no one told me to fix this problem. It was just something that we kind of stumbled upon. And so essentially what was happening was we had these huge hydraulic presses that were 2 or 3 stories, I'm talking thousands, if not hundreds of thousands of gallons of hydraulic fluid. And these things were old and the seals were leaky, and so the hydraulic fluid would just ooze down the side of these things. And then it would ooze down on the floor, and then it would be collected in these trenches, and those trenches it was essentially like a trough system, and then we had pumps that pumped all that to like a staging location. And then we would pay this guy to come out with the truck with a pump on the back, and he would suck all that dirty, grimy hydraulic fluid, and then he was getting paid like $7 a gallon to dispose of it. So knowing that, they were spending like close to $700,000 a year paying this random dude to come get rid of a problem, I simply asked the question, just as an intern, I was like, why don't we try to capture it before it ends up on the floor, or why don't we try to filter it or do something with it instead of paying this guy to mess with it? And so they kind of looked at me crazy, and to give you a little bit of background on like who we were working with, these guys didn't necessarily have engineering degrees. They didn't necessarily go to college. They were in their 50s and 60s. They hadn't had new thoughts come in this building in probably a decade. And so it was like, well, this is the way we've always done it. What do you mean? And so my idea was, I was like, well, I've taken all these classes on how to do wastewater treatment and land application. I was like, why don't we just use gravity? Why don't we set up a system with where we could separate some of the hydraulic fluid from like the water, because this was like an open trench, right? So when it rains, water gets in there. When they pressure wash the machines, that's how the water gets in there for that too. And if nothing else, we could at least reduce our volume so we don't have to pay this guy as much. And so then they were like, well, what do you need to set up an experiment or to be be able to test this theory. And so what we ended up doing is we actually buy soap to clean off these presses, and they come in like 400-gallon totes, these big plastic metal frame around them, and we just collect them, and they just get they stick them in the back of the factory until they get a whole bunch of them. Guy comes out of the semi and takes them off, and they like pay this guy to get rid of those too. It's like, why don't we just cut those open? My dad happened to work there. He was facilities, whatever, so he gave me the permission to chop these things in half. And basically what we did is we took a bunch of 400-gallon totes, and we cut like the top quarter off of like 2 or 3 of them, and then we set them up kind of like a staircase. And then we had just like a diaphragm pump that we hooked up to some air compressor. They'd just have compressed air all over the place, so we just like plugged it in with a hose. And so this pump would suck out this hydraulic fluid from the trench, and then we would pump it into the top one, and then as the top one would get full, the top part would run over to the one below it. Mm-hmm. And then as that one got full, same thing, then it would run over to the next one. And so eventually at the very bottom, you have, the hydro. In our case, at least, the hydro was on top. So it's an oil-based type, so it kind of floats on top of water. And so as you let it settle, all the hydro is staying on top. All of the solids, like gravel, crap on the floor, that would settle at the bottom, and then the water would be kind of trapped in the middle. And so we were actually capturing semi-clean hydro. And then at the very bottom one, then we would decant that off with and then we'd put that in drums. At first, that's what we were taking the guy to have hauled off. And we were able to reduce their waste by like 40% doing that. And then we came back around. We were like, well, how clean does it need to be so we can reuse it? And we were able to find by literally just contacting a company that deals with screens. And we ran it through like this special type of media that the hydro oozes through. And then we were able to completely recycle the hydro. And so that was kind of the solution. So ultimately, we took a $700,000 a year cost of this company, and we brought it all the way down to about $100,000. And they upgraded the system after we did kind of a proof of concept, which is kind of like an engineering term. It's like when you come up with an experiment and you want to go ahead and make it a permanent thing. You got to find the resources to be able to do this. And so we contacted a company that does nicer versions of this. They have like settling basins that are real nice and pretty, and they built like a system around it. They put some steps in, and so it was real nice. And so from what I understand, they went with it. They cut out a portion of a wall in one of the buildings and put this thing in. So there's like the stairs to it on the outside of the building, and then the system's directly inside that wall. So the problem was we were just wasting stuff, and nobody had asked the question, why are we spending so much to haul this off? And, honestly, the root cause on this one would probably be, why are the hydraulic presses leaking so much hydro? Not, why is it ending up in a trench so we can clean it? But as an environmental engineer, I have to rely on a mechanical engineer to figure that one out. I'd have to get one of my colleagues to look at that. But all I can tell you is there's a lot of ways that we can recycle things. It's not just cardboard. It's not just, aluminum cans and plastic bottles. There is absolutely recycling potential in industrial industries as well.
Okay, cool. So just abstracting away from the particular problem.
Sure.
So there was actually an existing solution to this problem, right? You have this dude who comes in and picks up the stuff and takes it away, right? We're paying him a lot of money. It's highly inefficient. So you see this inefficiency, and you're looking now to decrease. So now the problem now shifts from solving that problem to trying to get a better solution to that problem.
Yeah.
To reduce the inefficiency, to reduce the cost.
So engineers, at least in my school, one of the first things we learn is we learn about the fancy term of ROI, which is return on investment. And companies don't hire engineers unless there is money to be saved. Basically, that's what it comes down to. And so, as an engineer, your problem-solving capabilities is all limited to the bottom line. How can we save this company money, or how can we make this company money? So that's kind of what both of these situations, I guess. One was, more of a response using kind of a technical side. But what I find most interesting is the latter, which is the one that I learned at General Dynamics, which is saving money, saving resources, I mean, who knows what this guy was doing with it? He was probably just throwing it in the trash after we leave. So it makes me feel good to be able to say that, hey, like, we're able to conserve resources. I mean, yeah, we're saving the company money, but hopefully we're not wasting. So that's kind of cool.
Yeah. Okay. So you take a problem and you see an inefficiency and you're trying to reduce that, and then when you see that inefficiency, now you're trying to look for solutions to that, right? So what made you think of putting those gallon jars, the 400-gallon jars? Is there anything which you can point to which made you think of that over something else?
So, I mean, really what it comes down to is the school that I go to, I guess. So the school that I go to is in the civil and environmental engineering department. It's taught by a bunch of retired, we call them the white guys, but there are all these graybeards that all are professional engineers. Some guys built roads, other guys were a part of the 60s and 70s when we had a big expansion of building dams. And then others came from industry. At least at our school, all of our professors come from industry. None of them are your traditional PhDs, go straight into teaching and doing research. So they're all professional engineers. And so the problems that they give us from day one are all related to their career. So, if the guy that we're learning from in this particular class, he worked for the Texas Department of Transportation, a lot of his problems are going to be related to highways and, stormwater that run off from the streets, that type of thing. We have other people that they worked in industry. They worked for defense contractors, doing environmental-related Superfund site cleanups, especially. And so a lot of that, in that case, it's you want to kind of stop the expansion, the growth of the contamination. You want to go ahead and stop it before we know what it is. Like, I don't know what it is, but we just got to stop it. An example of that, one of the things that we've learned is with wells. You can actually use and this is common knowledge if you're familiar with the topic, but a lot of times what you can do is, say you have an Air Force base that has a flight line and those planes leak contaminants, and then it all runs off the flight line and then it gets into the ground. As it's soaking through the ground, it's permeating. What we can do is we can drill wells, water wells, and we can pump that water out at a fast enough rate where we lower the water table far below where the contamination is, as to prevent those contaminations from traveling through the water. And so that's what a lot of Superfund sites, the ones that I've studied at least, the examples that we've seen in class, they're like, well, we can't possibly dig out 1 trillion pounds of dirt, but we can limit the exposure and the growth of this plume effectively. And how we're going to do that is we're just going to pump out tons of water. And so that's one of the reasons why, if you look at every Air Force base, they have golf courses. There's two things they use that water for. One, they're using the groundwater. They're forcing the groundwater to drop really low underneath the flight line area to prevent contamination to continue to spread the plume. And so they take that water and they're like, well, what are we going to do with it? Well, we can just let everybody water their yards, and we can make a really nice golf course with it. And they also use it to treat wastewater. So when you use the bathroom, flush the toilet, they treat it to a certain standard, and then they discharge that as well. Because an Air Force base is just like any other smaller town. They're going to have to pay the larger municipality to get rid of it. So it's cheaper to go ahead and use it on site. So they'll water the grass with it, essentially.
Okay. Okay. So this particular problem, is it similar to the solution which you had for the?
Yeah. So we a lot of our classes, when we do like the design classes, they break it down through like the mechanics. You're looking at thermo and then like solids and fluids, and so you typically learn like the basics behind the theory, and then they start giving us real world problems to do homeworks and projects and stuff on, and then settling solids through physical methods is like a whole class. And so I'd already taken a sedimentation class. So to give you a little bit more background on like what I went to school for. So environmental engineering, our program is unique, and there's probably other programs out there like it, but we are specifically taking classes to learn how to design and improve wastewater and drinking water treatment plants. And so we do everything from like the pre-treatment of water before it gets there, to the sedimentation, coagulation, flocculation, and then disinfection, and then you have all the other more specific advanced treatment stuff. And so those are all the classes that we take. It gets all the way down to the point where we learn how to apply water on agriculture land, use land application. I would say that in that particular case, I was lucky enough to be far along enough in my program that I had already seen how we use physical methods to separate contaminants. And I recognized that, oil and water, they don't like to mix. And so if you give enough time, they will just naturally, through chemistry, separate. And then you just have to figure out, how are you going to take the one off the other. And so it was an easy process, but
okay. Yeah. So you're using knowledge which you learned in a particular context, and now you are using it in a different context, right? Yeah. So you're using it in the context of this particular general dynamics thing.
For sure.
So that's another aspect of engineering thinking, if you want to call it that, which is you have to be able to take things from particular contexts and apply them in other places, right? Solutions which you've already seen and apply them in other places.
Yeah.
Okay. That sounds...
It's fun, yeah.
Well, it definitely does sound fun. So just coming back to what engineering involves, so there are problems which you need to solve. In order to do that, you come up with solutions to those problems, such as the thing you did with the gallon jars or the 400 gallon jars or whatever. And then you mentioned something, you mentioned a proof of concept, right? You mentioned that, so now you need to, I guess, very cheaply test whether this particular thing is going to actually do what you think it was going to do, right? Because you're designing it without actually doing it.
Yeah.
Okay.
So my engineering field is unique in the way that there are so many variables that you have to take into account. So I like to give my brother a hard time. He's an aerospace engineer from Oklahoma State University, and the stuff that he does for a living, you can simulate a good majority of it using CAD softwares and some other things like CATIA and stuff. When you're dealing with things like temperature and environment and just random amalgamations of just waste, it's not like you're like, okay, I know exactly what the percentage ratios of this particular piece of metal are. I know that it's going to, when I press it and form it in a certain way, or if I heat it up a certain way, it's going to act like this based off its modulus. Like, we learn that stuff in like the lower level classes just to get a taste of it. But environmental engineering there's so many unknown variables. It's really difficult to be able to give a guaranteed solution without showing basically a small version of it. And so that's kind of one of the things that we do a lot in my program. We have labs completely dedicated to us just experimenting with random stuff. I mean, like, one of the classes I took for advanced water treatment, we were given our class was given a $5,000 budget from the department, and they were like, go online, we want you to find whatever you want to try using to clean this water. And then propose that to us. It's Amazon, wherever, show us the vendors, show us the best price, and then you'll work with your teaching assistants to go ahead and get that stuff purchased. We came up with random stuff. One of the things we chose, which was kind of funny, was we went through this catalog with all these different things for for fish with aquariums. Like, one of them was a UV water purification system. We had the question, would a water UV system for a fish tank, would that purify our water as a disinfection method for drinking water for us as humans? We bought one of those. We tried that. It works, but you have to circulate it for 24 hours in a closed system. So you're getting high contact for long periods of time of a UV lamp. What I'm getting at here is essentially you have to be able to MacGyver some of this stuff. You have to make basically experiments out of trash, stuff that's just sitting around sometimes, to be able to figure this stuff out. Other options that we could have done, which we did do before we purchased the equipment, we found a vendor, an outside smaller company, and we told them, hey, we know that you guys are specialized in the, whatever this type of equipment is. We're going to bring you a couple of water samples, and we'd bring them a 55-gallon drum of it, drop it off, and we'd say, tell us how you would recommend us to, clean it. And then they're always going to sell you the Cadillac of whatever, the most expensive thing you can come up with. And so then being the engineer on site, your job is to go back to the bosses and say, hey, this guy's full of crap. He's going to give you, this $100,000 solution to a problem when we could do it for $10,000 in supplies and a little bit of labor. If that's what you want to do, boss, we can go ahead and do that. But I'd recommend something, a little less advanced. So that's kind of one thing.
Okay, that's pretty cool. So what you're doing there is, so you're taking something small, and so then there's the aspect of scaling, right? Because you start with you're doing a small experiment on with a small setup, and then you need to scale it up. Can things go wrong in that process?
Oh, for sure. One of the things we had to tweak was our inlet for this particular process. If your volume coming in if your flow was pretty fast, it mixes up the water, and so then you're not allowing for the settling effect to happen. So what we actually did was we took basically a metal, I don't know, I would describe it as a weir, but essentially what it was a box. And we attached this to the end of the hose, and then we submerged that down to the bottom. And so that when the water comes out, it hits these three sides of this box, and then it forces the water to kind of tumble a little bit and then kind of float out slowly. And then in this long box tubing, what it was 4-inch by 4-inch metal, just scrap that we had found. We stuck the hose on one end, drilled a bunch of holes in it, and so then the water flows in, and then it seeps out of those holes, and so it keeps the water, this liquid and laminar flow, because we don't want to disturb the water. We also had issues based on the size. We needed to be able to store some of the excess, because once it started working, the night shift was like, great, we have a solution to getting rid of all this crap. And then they were just completely contaminating the system. What I mean by that was they were overfilling it too fast. And so then the physical processes weren't able to take place because we needed it to settle, take time. So it needed to just kind of trickle in there. And so there was a lot of flow rates that we had to calculate based on the size. I forget exactly what it was. It's been a few years, but it was something like slower than 3 gallons per minute, GPM. If we kept it below that, then we found that it worked best. When it was scaled up, what you had is basically we call it a tank farm. And so there are these big storage tanks, huge, the size of houses. And we had one of those that they used. Basically, they just dump it into that, and then as it would fill up, there was like a little bobber in there, and they would kick on that pump, and that pump would draw from the bottom, and it would send it over through this PVC piping over to the treatment staging place, and then from there, it would go through the process. And so we were able to figure all that out by fine-tuning it, and basically this thing would run autonomously without an individual watching it. The thing you have to be careful about, though, is regulatory agencies. And so the key here is that we were not treating the water, because treatment means that you have a permit to be able to treat that water. What we were saying is we were polishing the water. It's just like semantics, honestly. But what we were doing is we were just making sure that the contamination that we had, the hydraulic fluid leaking from the presses, we were keeping it at its pure state of what we were getting it from the source, so that we could handle it without all the other contaminants. And then, of course, you got to factor in cleaning and disposal, and there's all these different, and you have to have contingencies. For example, what if it stops working, or what if the night shift does decide to overfill your system? What engineering controls do you have to be able to predict that something went wrong and to stop it from happening? So, where was the water going? We were recycling it back in so we could reuse it. And it would go through a filter press. Essentially, it was just we pump it through these certain type of filters, and then it would ooze through all these different layers, and at the very end, it was pretty clean hydro. And then we would take that hydro, and then it would go back over to where we insert the hydro back into the stuff. So it was kind of just a recycling process, trying to limit the amount of waste.
Okay, that sounds pretty cool. So now when you're when you're taking something and you're trying to scale it up,
Yeah.
So one of the you're starting at a smaller scale. You're starting with something small, and then you try it out and so on, and that allows you to take it to a larger scale and so on.
Yeah.
So what the role of an engineer in that is to like narrow down onto possible solutions, right?
I guess.
So there's a space of an infinite number of solutions to a
Yeah.
particular problem,
Yeah.
right? I could randomly come up with solutions to problems. 99% of them won't work, right? So what you're using your expertise for is to narrow down that range of solutions. And that you base on your understanding of chemistry, of biology, et cetera, et cetera.
Yeah.
And then once you're in that constrained space of solutions, that allows you to, now those are the ones you test out, right? Those are the ones you actually play with.
Yeah.
And then a subset of those
To hit back
scale.
on the one thing you'd mentioned, I don't think I quite was clear in my last comment, was about like the scalability of things. And so, like, obviously, engineers, we learn to install like safety factors. And so, if you know you need 500, I'm just making up a random number, 500 gallons, then you would say, well, I need a safety factor of 2, and so you would factor that in, and you would make it a little bit bigger. So yeah, there's a little bit of planning. You can't just design things without knowing. So, what's our operational capability? What's our waste incoming flow rate? How much are we getting? What's the production like in that particular period of time? Were we in low production? Were we using these presses a lot? What's the worst case scenario? Like if I was running these presses every single day, every single week, and we were getting rain every single day, like what would that look like? What would that event look like? That's what you would want to design it for. And then you'd have to factor in things like space. I mean, there's just so many different things. You need industrial engineers to help you determine some of that. You're going to have to get tradesmen in to help with some of that. So scalability can be really difficult. Like when you're doing water treatment plants, you typically look out 20 years in the future, and you're like, hey, in 20 years, what's the population going to look like? How much water are we going to be expecting that we need to treat? In a manufacturing setting, it's a little bit different because your workload is a little bit more limited. So you could say, let's look out 3 years in advance. 3 years is typically your return on investment anyways. So any engineering design that you recommend, you typically want it to be under 3 years of return on investment. And then once that happens, then you can look at better, you can look at that Cadillac type product. But cheaper isn't always better. It's more about, just making it easier on the guys that are producing the parts, making money for the company. There's always time to innovate. And so what you want to do with that is you want to make sure that you collect data throughout the process. You want to keep good contacts with stuff. Lean manufacturing, I don't know if you've heard of that term before, but it's kind of related to Six Sigma. Some people like it, some people hate it. In my school, we learn it. So it's a class we take. We take that and we take engineering ethics, both of those. And so then you kind of learn, and that's where everybody from my school, the reason why projects are so easy at my school for us to solve is because we're all taught to use lean manufacturing. And so the problem-solving aspect is very clear-cut for all of us because we all know, okay, first we have to visualize what the problem is. We need to, draw a process map and figure out, all the different variables that are coming in there. And once we've identified those, we want to look at, like, the risk assessment codes. And the risk could be like, radionuclides in water, or really, really acidic or really, really basic water. I mean, those are going to determine the types of treatment that you can use. Is there a lot of sediment in it? I mean, there's just so many different variables. It's kind of fun. It's like the ultimate puzzle. And so when we do these design classes, I think it's enjoyable. That's why I was able to get a master's degree, because I found it fun. So.
That's okay. So one of the other things which you talked about briefly was other people making errors when using your equipment, right? And you need to plan for that.
Yeah.
That's an interesting thing, which is kind of peculiar to engineering, and areas like engineering.
For sure. The best way I can describe it is like, imagine playing with Legos and you're following the Lego diagram the exact way that you told them to do, and then all of a sudden they just start putting parts together that don't belong, and they're adding pieces together that you're not supposed to use yet, and then they just throw things together out of order, and it could cause things to fail. At least in the manufacturing side, we rely very heavily on our operators, the hourly type people that are carrying out the process. So typically, most places will have work instructions, which is the item that the operator uses on a daily basis. So work instruction could be, it's literally step by step, like Lego diagrams. So even if they're not good at reading, it doesn't matter, just follow the pictures. They usually don't mess up. And then it's very specific. If you run into a problem, if you don't see something exactly like this, come get us before you make a decision. Because they might make a mistake and they could get hurt, or they could cost us lots of money, or they could bring the assembly line down completely because they broke something. And then the next thing you have is manufacturing procedures. A manufacturing procedure is a little bit more broad than a work instruction. A manufacturing procedure is typically using a particular piece of equipment. So in this case, I had to write from scratch a manufacturing procedure on how to use this water treatment system. We would determine who gets to use it, who's allowed to use it, what things to look for, to be able to specifically write out, this is when it's running right, this is what you should expect, and when it's not working right, this is what you should expect, and then to show examples. So it's kind of fun because in those, you get to sabotage yourself. You get to show what it looks like when the system's overflowing, or when the hydraulic fluid's being mixed in with the water. Like, what does that look like? How can we tell that it's not working right? So you do all that. And then, of course, you have things like pH, and we had basically take a water sample, and then they stick it in this machine, and it stirs it, and there's like a little probe that goes in it, and it tells you what the solubility is of it, how much water to unknown contaminant ratio it is. So it's little things like that. But yeah, it's definitely, people will always mess it up. And so as an engineer, especially when you're dealing with water treatment, I feel like they're always on call. They got to come in on weekends. Stuff breaks. You got to, everybody's, so that's another stressful thing about it too, is in some factories, if the engineers can't fix it quickly because they have to wait on a vendor to come in and fix it for them, then the assembly lines get shut down, which means those hourly guys have to go home. That means their paycheck's going to be smaller this week. So it's very, very stressful, and people get heated about that. It's a lot of people live paycheck to paycheck, and so you don't want to be the engineer that causes that to happen. And also engineers also have to be really good at managing their managers. So your managers are the people that give you money to be able to make promises happen. So that's also something that you have to. I guess one of the stereotypes about engineers is a lot of people think they're geeky and nerdy, and they might be their freshman, sophomore year, but by the time you graduate, by the time you have experience, so far I haven't met at a kind of your weird geeky. We're all kind of weird and geeky, but like the really awkward, antisocial, quiet. Those don't really exist in the realm that I work in.
That's actually interesting because so you have to deal with a lot of people, right? In a lot of different situations, you have to deal with your vendors. You have to deal with the people who are going to be using your whatever you create. Yep. You have to deal with the people who are giving the money to you to be able to create the stuff, and probably many other sets of people. Yeah,
you got your managers telling you that they want shit done, and you're like, okay, well, let me try to get this figured out. And then you get the vendors that are promising you everything under the stars, and they're trying to get as much money out of you, and so you can't trust them because they're basically telling you a fairy tale. So you have to be careful with them. And then you have your operators. Some of your operators are going to tell you how it is. Other ones are not going to talk to you at all because they're afraid you're going to get them in trouble. And so it's I don't know if it's a sociology term. I can't remember maybe it was sociology. Code switching. There's basically that's just it's how you talk to people.
Okay.
So when I talk to an operator, I talk to him like I'm an operator. Tell stories about your kids, cuss a little bit. You're just hang out. If whatever it takes to kind of figure out what they're doing. for them to kind of trust you, and then to always sell your solutions in two ways. One, to save the company money, but to also make the operator's job easier. Operators will help you if they're getting something out of it, meaning that they are making more product, which means they're going to get potentially a promotion or a bonus of some kind at the end of the year. They're going to hit their HPU, which is just like the hourly part unit, which is like how many parts they have to get during that certain period of time. But at the same time, operators are typically told by their leadership that they should not be talking to engineers because they need to be working. So you have to figure out when are they available to provide feedback, and then you have to communicate back to their supervisors, their line leads, hey, we need to make sure that we set aside time for them to be able to talk to the engineers. And then again, you have to go back to your managers. Your managers are they're stressed because they just want to get product out the door. They don't really care about the solutions, I feel like. I'm young in this career field and all that, but to me it kind of seems like they're more worried about the dollars, which is good. That's the reason why we have them in that position. My job is to make you more dollars. So you have to be very, very data-driven to be able to be convincing on why we should move in the direction we want to move, and then get buy-in from multiple people that have more experience than you, people that are specialists at vendors, your peers, if there's more than one engineer in the same area. You should never make a solution with just one person's ideas, and for that matter, you should never solve a problem without collecting data on that problem, because who's to say that the symptoms that you're seeing are related to the issues that like, for example, the problem you see, like you had mentioned, you might think there's all these different variables that are attached to it, and I might only see one. If I just try to fix that one, it might work for a little bit, but then the problem might arise again, and then we might have just invested all that money into a solution that doesn't actually fix the problem. And that happens at every big company for sure, because you have to characterize you got to use lean manufacturing. You got to do factory dynamics, which is just like, it's a holistic approach to how you run a factory. Okay.
So you've mentioned lean manufacturing a few times, so it would be great if you could expand upon what that is.
So lean manufacturing, I don't know who came up with it. I know that Boeing, Raytheon, General Dynamics, Banks, everybody. I guess Banks don't use lean manufacturing. They use like Six Sigma. But it's basically just tools that we use. Things like a gimbal walk, which is just a weird word for I think it stands for the actual place. I can't remember. Essentially what it is you visualize the problem, you get a team together, you get all people that are in this team, you get them all to commit to solving the problem. Some companies, they call that a circle. It's basically you have one person that's a coach, then you have subject matter experts in different areas. From there, you prioritize how every person's going to contribute, right? Because you don't want one person to come up with all the other ideas and everyone just sitting at the table just shaking their head, yes, yeah, that sounds good. Everyone needs to come to the table with something unique, potentially addressing the areas that they are most experienced in. And then you want to characterize, that's going to come up with a solution to collecting data. Data things could be, 7 wastes, which is a tool. It's a Six Sigma tool, which you look at defects and overproduction and weighting and inventory and the motion, which is an operator, how many places does he have to move? Is he having to pick stuff up, or is she having to pick stuff up? And then walk it down the line, or can we automate that? And then processing, how much labor does it take to do one thing? You have failure modes, effects and analysis. That's another tool. That basically just looks at risk assessment charts, and it tracks different objectives on some of the issues. And then you have failure and severity calculations. And so what that does is it allows you to prioritize the worst effects first, solve those, and then work your way down. So if there's a single point failure in a particular process, you probably want to fix that before you worry about making sure that the floors stay clean, little things like that. But yeah, lean manufacturing is just the idea. There's a lot of different things. It would take an entire class to learn on. I'd have to have notes in front of me, but just from my memory, it's essentially the idea is you want to mitigate waste. You want to, if your goal is to produce this one piece of hardware, then you get one item coming in and then one item coming out of a finished product. And then every hand that is collecting a paycheck on that assembly line makes a positive impact on that. So if you don't need them, then they shouldn't be there. They should be doing something else. And then for everything that is labor intensive, that can have human error, which human error is a terrible excuse. You usually get your wrist slapped if you talk about human error in most places. But typically, it's not the operator's fault. It's like it could be like a highly repetitive process, or it could be subjective. Like there's no clear way to tell if something's right or wrong. And a good example of that would be like inside piping or tubing. If there's no way for the operator to look inside there and verify that it's good on the inside, it's clean, then how can you expect them to sign off on it to say that it's good to move on? And so you'd have to come up with solutions to determine that either at that station or before. And it's just lots of tracking, but ultimately lean manufacturing is good because it eliminates waste, increases speed of production, and then it's your best opportunity at bringing in things like automation, assembly lines. Toyota is a great example. They're some of the best at it. Boeing, building aircraft on like literally assembly lines that are traveling, that type of thing. It's kind of cool.
Okay. So I think earlier you had mentioned that there are some people who don't see value in lean manufacturing.
Yes.
What are their objections?
So it depends on the world you come from. So to me, me personally, I'm kind of a rule follower, always have been. So I'm like a believer, I guess you could say. So when I learn this stuff in class and when I've gone through like Six Sigma training, I'm like, wow, this stuff's awesome. To me, it's opportunity for to get your name on new projects because you're collecting the data, you learn the impact, your return on investment. There should be no reason why you shouldn't. But some people, they just want to fix the problem and move on to something else. They're kind of the minimalist. And using lean manufacturing and Six Sigma is very time intensive. And so if you're in a stressful position where you have a lot of work to get done, you don't have time to sit down and fill out an Excel spreadsheet or to collect your data samples and to build a report and to assemble a team and then get buy-in from people that don't even know your process that are going to slow you down essentially. Because some problems, honestly, can be fixed by one person.
So that's the main objection.
Yeah,
okay.
Yeah. And so some people are just like, it's a waste of time. There's no value added. And so they're looking at it from the same way that I'm looking at it from an operator, right? I don't want my operator to touch anything unless it's value added. But they're looking at it as if they're the operator. I don't want to fill out any paperwork unless it's value added. The thing is that might be a little short-sighted because if you're to do lean manufacturing on everything that you touch, yeah, you might not get as much work done, but the work you do have, you're going to have data to back up every decision you made. And there's two things it helps you with. At the end of the year, you can add all that up, and then you have one big, this is how much money I contributed to the company. And if you're award-driven or if there's bonuses that get allocated to your company, they need some kind of a discriminating factor for you and your peers. You want that data because they're going to challenge you on it as soon as you bring it up. I saved you guys $25 million this year. They're going to say, how? Where's the data? And so if you start collecting it from day one, it takes a little bit slower to accomplish projects, so be it. So that's kind of the difference. Some people, they aren't. Some people, they're not goal-oriented. They're not award-driven. They just want to collect their paycheck and go home and play video games, play with your kids, take naps. So it really just depends on what you want to do. Do you want to be a manager someday? Because that's what managers are going to be asked to do, is managing data, managing trends, that type of thing. So that's where I want to be someday. So that's why I'm a little bit more focused on it.
Okay, that's pretty cool. So what I want to do now is you've had a relatively pretty interesting life. You were in the Air Force, then you've gone back to study, and now you've interned at a few interesting places, and now you're going to be graduating pretty soon, right? So can you just take me through your history from your undergraduate to now?
Sure, yeah. So I graduated high school in 2010, went to Texas Tech for 1 year. I wanted to be a civil engineer. My parents are just like most people in America. We're were barely middle class. They couldn't afford to help me even with rent. And so I found myself working a bunch of part-time jobs just to be able to pay for school. And that was even I'm talking just to feed myself and pay for rent. Because in the dorms, at least at my school, it's like, if you do the math, it's like $900 a month to stay in the dorms. Wow. So, and that, it was too expensive and I couldn't afford it. My parents were already hurting themselves. So I didn't really have any financial support. So basically what happened was I got to the point in my life where I was like, I know I want to be an engineer. Like, I was so inspired by it. But I wasn't a strong academic because I was not studying. I was busy working all these part-time jobs. And so I had to make a decision because my brother is 3 years younger than me, and he was trying to go to college too. And I knew what was going to happen because this was a conversation we were having with our parents. Was they were basically asking me to drop out at Texas Tech and go to a community college so that my brother and I could both like work and pay for our classes one at a time. And so I kind of had that big brother moment where I was like, well, I really want my brother to be able to go to college. And our grandparents were willing to co-sign, but they don't really have credit because they're farmers and they own everything they've had and they're retired. And so we tried getting them to co-sign on both of us, and it was not enough to cover either of us to go to college. It was enough to cover one person if there was only one person co-signing. My parents they don't have the best credit history, so they couldn't really co-sign on anything, which made things worse. So I made the decision to enlist because I knew that there was education benefits involved, and I knew that I was going to be wiser and harder working and more disciplined once I had military experience behind me. And knowing that I wanted to be an engineer, I was worried that I was going to have to settle for a lesser degree in something like business, something that I knew that I could be successful at, but that it wouldn't be like what
you want to do.
Yeah. And so, long story short, joined the Air Force, did really well. I got the job I wanted, which was bioenvironmental engineering. Did industrial hygiene and preventative medicine. Got to deploy and do a bunch of chemical weapons search and seizure. That was pretty neat. I did 4 years, actually 3 years and 9 months. I left early just because I had really great mentors that encouraged me to go back to school. And I had the buy-in from my wing commander who was willing to let me start school in the fall because I was going to end my enlistment in October, and so I was going to have like a couple of months. I just going to have to wait until January to start school, and so it would have been a couple months where I wasn't collecting a paycheck but still had all these adult bills to take care of. And that's the hardest thing I think about leaving the Air Force is, you accumulate all this like routine debt, right? Your cell phone and your living expenses, your car payment. When you go to college, there's not really anything to help pay for that. So unless you own everything outright, a lot of veterans, they go back living with their parents, believe it or not. Wasn't going to do that. My parents were going to let me come home anyways. So I went back to Texas Tech. I chose Texas Tech instead of another school. I probably could have gone anywhere I wanted. I did some campus tours, a couple of different schools. One of them was Yale. Didn't really like that one. A&M, UT. I really was what made me go back to Texas Tech was because I had some different classes there. And when I went back and toured, professors actually reached out to me and gave me like a private tour. They were like, oh, yeah, why don't you come back here? And they were, former civil engineering, Air Force officers back in the day. They found out I was coming back, and they immediately became like my best friend. They were like just showing me everything, and I really felt special to them. And so that was the reason why I came back. And then I was going to do civil again, but then I heard about environmental, and that was kind of what I did in the Air Force. And so I wanted my military experience to complement my degree, which would also support my civilian career. And so then I decided I wanted to do internships right away. Defense contractors obviously like military. So I did 2 internships at General Dynamics, and then I did an internship, a co-op, and internship at Raytheon. And then that's it. That's pretty much everything I did. One thing that's unique about me that most veterans don't do is I'm a big believer in professional development and leadership. And so, I was just a young guy in the Air Force, made E5, and then immediately got out, so I didn't really get any leadership experience from like a traditional system. A lot of it was like volunteerism leadership. And so when I came back to school, I made sure that I, ran for, clubs, ran for the president roles there, and I worked my way all the way up to graduate vice president for the student body. So it's was involved in like student government the whole time, and I found that being in those leadership roles not only made me a better student, but also was able to help me mentor people around me. And it's only made me a more successful student. I think I took that military mindset of being strict and disciplined in everything I do, and kept things professional. I'm not just wasting away at home, chilling. I mean, I feel like I'm making an impact on campus. I give campus tours to incoming engineering students, do all that type of stuff. So, I'm excited to graduate. I feel like I've been in school for a few years now. Getting a master's degree in environmental engineering has been a 10-year goal for me ever since I left in 2011. So I'll be graduating in 2020, and it's pretty exciting to be able to say that you can complete a 10-year goal. I feel like most people, their goals and priorities in life change in 10 years.
Yeah.
And so you don't unless you're getting a PhD or something, then maybe you'll accomplish a 10-year goal. But I feel like most people, they just move from one goal to the other. And it's difficult to predict, what's going to be meaningful to you in the future. So it's been a fun ride. I've really appreciated all the opportunities that have been given by both my employers and friends and professors.
Cool. So one thing which I do have to touch on, just because it's pretty funny, is you were on ISIS hit list. Not just funny, it's kind of scary as well. But
yeah, it's not too big of a deal. So basically how that happened was, I want to say it was 2014. Yeah, it was the beginning of 2014. It's been a while. So, long story short, essentially some idiots on social media, they decided it'd be really cool to create like a top 100 ISIS hit list. And there was absolutely no intelligence gathered to build this list. And so what I mean by that is so the bad guys know what planes fly over the combat zones, right? And so they're like, a B-1. Where do the B-1s, where do those go? Oh, Dyess Air Force Base. Okay. And so then they Google Dyess Air Force Base. Common knowledge, right? You see pretty pictures of B-1s on their website pages. Well, at the same time, I had won a bunch of annual awards, had some really cool pictures that our public affairs officers and Corps were so gracious enough to write news articles about me and to celebrate my accomplishments. Those same pictures and awards were also the first thing that you Google, and since I have a unique name, I got thrown on the list. It was a big deal when it first happened. Now the bad guys are essentially gone, and then every so often, now there's one that had 2,000 names. There's another one, you look, there's like 8,000 names. They just keep adding and growing and growing. It was kind of interesting, like how I got put on it. But just guilty by association.
How did you find out about it?
So I was doing part-time school. I was working up on my military base, and I had a really nice cubicle at work that had dual monitors and no distractions. And so I would go up to the office on the weekends to work on schoolwork. And we were actually planning our officer, I want to say it was a birthday or something, I can't remember. Anyways, we had a bunch of balloons and like, funfetti and stuff. We were just gonna trash his office with it. So I was actually filling balloons, and I get a phone call from my first sergeant, and then I'm like, why is he calling me? Didn't answer. He calls me again like 30 seconds later. I'm like, well, it must be an emergency if he's repeatedly calling me. So I answer it. I'm like, hello? And he asked me where I was at, and I was like, up here at work, working on schoolwork. Why? And he was like, okay, I want you to stay there. I need to come swing by and talk to you. I need to pick you up for something. And that's all he said. And so I figured somebody had said something on social media, or, that they knew we were going to be pranking our officer, or worse yet, there was some enlisted party that somebody got in trouble at, and somehow my name was thrown in there. Since I had our first sergeant was a let's just say that he was always over at our area, because we had a lot of really good airmen over there, and so we won a lot of awards, and so he was really well connected to our flight. A flight's kind of like a smaller specific unit, okay. All of the bio people. And so he used to come around and hang out with us all the time. We had a heritage room and all that. So we had a good relationship with him. So I'm waiting there for him, and he like rolls up, and it wasn't his car. It was our group commander's Cadillac, and our commander's driving, he's in the passenger seat, and they roll up to the building, and they come knocking on the door, and I open it, and they're like, hey, I don't know if you've heard, but you're on this list, and we need to go brief you at the OSI office, which is Office of Special Investigation. I was like, okay, all right. And so just in civilian clothes, we hop in the car, we drive over there, we go to the med group first, and our commander gets some stuff out of his office. I think it was like a notepad or something. We walk in there, and there's like a basement. I didn't even know there was a basement existed in this building. So there's some like random door. We go down there, and it had everything from like my MySpace to my Facebook. It had my LinkedIn profile. It had all the news articles that had pictures of me. It was everything. And they had been assessing pretty much all of my social media, and they told me that I was on the list. And so wasn't really a big deal at the time. I mean, there was hundreds of other people. There was a couple other people at our base that had also been on the list because of the B-1 situation. It didn't really frighten me at all. Wasn't concerned about it. It definitely frightened my parents, though. They weren't very excited about it. So I don't really, it's not really newsworthy to me anymore. It was a little scary, a little exciting, made you feel kind of like a celebrity for a little bit. But then you realize that it hurts people's feelings when you do that to people. So people like to be recognized for positive things. I'm hoping that they've decided to change what they do, at least in the Air Force. It's a good idea to maybe not post a bunch of PR articles to the public where people can find that out. Me, it was an issue. My parents have never moved from the house we grew up in, and that's very uncommon. And we have a really unique last name, so that made it even easier to track us down. So moral of the story is move frequently, either upgrade, promote, whatever. Pay to have the services where they remove you from yellow pages, white pages, whatever. Keep all that information secret, because you don't want people to be able to Google where you live. It's just not a good idea.
Cool. Okay, thanks a lot for that, Adam. And if there's anything else you want to add, or
no, I just really appreciate your time. It was fun talking about problem solving and random Air Force stories. So good luck, and we'll talk to you soon.
Okay, thanks a lot, and good luck with your graduation and what's to come after that.
Thanks.
Unless you forwarded to the end of the podcast without listening, given that you've arrived here, assume you found the podcast at least mildly tolerable. Assuming that is the case, please subscribe to us on Apple Podcasts, Spotify, or your favorite podcast app, and share the podcast with those who you think may be interested. It would also be great if you could rate the podcast on Apple Podcast. Assuming you give it a good rating. That really helps others discover it. You might also enjoy visiting ThinQ's website, www.think.education. ThinQ is spelled THINQ. There you will find articles, videos, and educational material which aim to develop inquiry and critical thinking abilities. You can also follow ThinQ on our various social media channels to get updates on webinars, courses, and new content. I would like to thank Vedant Chandra for the theme music and Malika Nanda for the podcast artwork. See you next time.